modulus of a complex number, and then we'll be moving on towards division of two complex numbers. So the first thing for ourselves to do is just a quick reminder for all of complex numbers. Obviously with the last video we saw that it is a combination of real numbers and imaginary numbers, and they form the complex number. They always come in the form a plus bi, so a is 2, b is 3, and then I is just I. And that is their typical format. Obviously a and b can be positive or negative numbers. They're elements of the set of real numbers. So now, what is the modulus? The modulus is essentially just a measure of distance. It is what we find when we plot a complex number. So I'm just going to flip over here. So I had a complex number, I've labelled it Z here, and it was the complex number 2 plus 2i. Okay, that's it there. And if somebody were to ask me for the modulus of this after I've plotted it, essentially what they're asking me is, if you were to draw a line segment from the origin, the point 0, 0, to wherever this complex number is placed on our Argand diagram, how long would that line segment be? Alright. The formula for the modulus of a complex number, it comes in the form of the modulus of z in this instance is equal to the square root of a squared plus b squared. And obviously we know that all of our complex numbers come in the form a plus bi, so that's where that a and b are going to come from. Now people might wonder, where did they pull this formula from? It's based around trigonometry and our theorem of Pythagoras. So we can see what I've done here is I've plotted the point z, and I just dropped a vertical line straight down to the real number axis. And what that has done for me is it's created a right angle triangle. Okay, we can see here that this is 2 units. Okay, because obviously it's 2i, we've gone up 2 on our imaginary axis, so it's 2 units up. And also if we were to think about its horizontal length, it's going to be 2 units across, because it comes out 2 units on our real number axis. Okay, so we know with our theorem of Pythagoras that basically it states that c squared is equal to a squared plus b squared, right? And if we wanted to somehow relate this to what we have here, well, if we squared both sides, what we should be left with is that, you know, square root of c squared, well, squaring and square root are opposites, so that should just leave us with c is equal to the square root of a squared plus b squared. So that's very briefly how that formula is derived. Okay, that's not a very in-depth explanation, but it's good to know where these things come from, and hopefully that can help us understand it a little bit better. Alright, now what we have here is just an example of finding the modulus of a complex number. I'll go through this example and then I'll do another example afterwards as well, and hopefully we can get a more complete picture from those two examples. So again, modulus of complex numbers, it's going to be the distance of, or the length of the line segment from the origin to wherever that complex number is plotted on our Argand diagram. Our whole foundation for complex numbers essentially is that I squared is equal to minus 1. Here's our formula for our modulus. That will not be given in the log table, so it's something that we do have to learn. And then for this example, I've just picked the complex number 2 plus 3i. Okay, and I've plotted it out here. So what we're looking for is the length of the line segment from the origin to Z1. So first things first, what we should do is let's just label our complex number. We know it comes in the form a plus bi, so obviously that means that our 2 is a, our 3 is b, and then obviously our I is just I. Okay, and now let's slot it into that formula there where we have the modulus is equal to the square root of 2 squared plus 3 squared. Alright, these are relatively easily calculated. Square root 2 squared, or 2 times 2, that gives me 4, plus 3 squared, 3 times 3 is 9. Okay, so the modulus of Z1 in this instance is equal to the square root of 4 plus 9, which is square root 13. So that is the length of the line segment from the origin to the complex number. So from the origin to the complex number, the length of that line segment there is square root 13. And of course we can find that as a decimal too if we wish. Okay, so here's another example. I've labelled this complex number as Z3. Its value is -4 plus 8i. Here we have our formula for our modulus of the complex number. So our first step here is going to be just label our complex number. Obviously -4 is going to be our A value, 8 will be our B value, and then I will just be I. And they all come in the form A plus BI as we have discussed. Okay, so now it's just a case of putting in these values. We know that modulus Z3 is equal to the square root, part of our formula here, of -4 to be squared plus 8 to be squared. Now something we should hopefully know about distance is that it's always positive. So we should never have a solution here that's a negative number. And that's why we have our absolute value signs around our Z3 there, but we know that you can never travel or measure a negative distance. So the distance of the length of the line segment from the origin to wherever the complex number is should always be a positive number. Right? So again we have Z3 is equal to square root. Well, we know that -4 squared, any number squared will give us a positive number. So -4 times -4, well, that gives us 16. Okay, and then 8 squared, well, 8 times 8, that gives us 64. We can tidy this up again. Modulus of Z3 is equal to the square root of 16 plus 64, so that would give us 80. So Z3 is equal to the square root of 80. We can, of course, find this as a decimal, and if we were to do so, the square root of 80, what we would find is that or Z3 is equal to 8.94 rounded to 2 decimal places. So the length of the line segment from the origin to this complex number Z3 is 8.94 units. So next up we have the conjugate and division of complex numbers. And these two go hand in hand for the most part. What we have here just in front of us is two complex numbers. We have obviously Z there, and it's 2 plus 3i. And then we have Z2, and that's -4 minus 6i. So if we were to think about the conjugate of these two complex numbers, well, first of all, the symbol for the conjugate is just that, Z, with a horizontal line above it. And what the conjugate is essentially is it's the same complex number, but we have changed the sign of the imaginary part. So we've changed the sign of the BI, because obviously they all come in the form A plus BI. So the conjugate of 2 plus 3i is actually 2 minus 3i, okay? And what I would do is encourage you to pause the video here and see if you could write out the conjugate of Z2. If we move on to Z2 there, what we have is Z2 conjugate. And the conjugate of this, again, we're changing the sign of the BI element, or the imaginary part, and that would be -4 plus 6i. So this is a rule that's very much instrumental to our success for the division of two complex numbers, or the division of a complex number by another complex number. It won't help us for division of a complex number by a real number, but it is hugely important for division of one complex number by another. So it's something we have to remember. There's nothing about it in our log tables. It's just a little trick that will come in handy for us, and we'll see in a few minutes how it can work to help us. And here we have two examples of division of a complex number by a real number. So the first one there on the left, we have Z4 is equal to 15 plus 10i divided by 5. And then on the right hand side we have Z5 is equal to 8 plus 36i divided by 4. So let's start on the left hand side here now. We have Z4 is equal to this. So all we really need to think about, and This is far simpler to approach than what we'll see in a moment or two. All we need to think about here is that to simplify this, how many times will our denominator go into each element of the numerator? Okay, so how many times will 5 go into 15? Well, 5 goes into 15 3 times. How many times will 5 go into 10i? Or another way I suppose we could think about it is, what would I need to multiply 5 by to give me 10i? Well, 5 goes into 10i 2i times. And that is our simplified answer there. That's our solution to the division of a complex number by a real number. Again, I would encourage you to pause the video and attempt Z5 here on the right hand side. Okay, and if we go ahead with Z5, what we see is, again, we're considering how many times will our denominator fit into each element of our numerator. And what we have here is that 4 goes into 8 twice, and then 4 goes into plus 36i 9i times. Now these two examples are really straightforward. I picked them for their simplicity. Obviously everything here divided in evenly, which is fantastic, but that's not always going to be the case for us. Now we have an example here of a complex number being divided by another complex number. And this is where we will be referring back to our conjugate of the complex number. That's what's going to be instrumental to our success in solving this. So if we just remind ourselves of what that looked like, it was that if z is equal to 2 plus 3i, well then its conjugate is 2 minus 3i. So we're changing the sign of the bi part, or the imaginary part, okay? So we're posed with this question here. It's that z1 is equal to 3 minus 2i, z2 is equal to minus 4 plus 3i, and they want us to find z2 divided by z1. So I've just kind of written out our two complex numbers here as numerator and denominator. Okay, so this can be difficult because initially when we look at it, we see that obviously with our complex numbers we have real parts and imaginary parts on both the top and the bottom, and it's extremely difficult to consider how they might divide in a practical manner into one another. So we have a little trick for this, and the trick is, the first thing we need to do is identify the conjugate of the denominator, or the number on the bottom of the fraction. Okay, so in this instance it's going to be the conjugate of z1, and we can clearly see that z1 is 3 minus 2i, so its conjugate should be 3 plus 2i. Okay, and now that we've identified that, we will be able to use it effectively. And when we use it, what we should find, if we've done things correctly, is that we'll get to a point where there are no longer any imaginary numbers or I values left on the bottom of the fraction. Perfect. So the next step now, we can see I still have my fraction. I've extended out the line there because this is where I use my conjugate. So I take my conjugate, and what I need to do now is multiply both the numerator and the denominator by the conjugate of the denominator. So I'm going to multiply the bottom by 3 plus 2i, and I'm also going to multiply the top by 3 plus 2i. And by doing a top and bottom, I'm ensuring that it as an expression is still the same, because I'm treating all parts equally. And now it's a case of multiplying these guys out. We can obviously do our binomial expansion or our array method if that's what comes to you in an easier manner. And once we multiply out top and bottom, we can see clearly there that the top has become minus 12 plus 9i minus 8i plus 6i squared. Obviously we had 3i times 2i, that gives us our 6i squared. And then on the bottom we have 9 minus 6i plus 6i minus 4i squared. So let's tidy this up a little bit. What we have up top is our minus 12 stays the same. We have 9i, take away 8i, that leaves us with just I, or 1i, and then we have plus 6i squared, okay? And then on the bottom, what we have is 9, stays as is, minus 6i plus 6i, well 6 takes 6, that's 0, so those guys cancel for us, and then our minus 4i squared stays as is for now. Now looking at this, it looks somewhat tidier, but we're not fully there yet. The whole foundation of our complex numbers, hopefully we can recall, is up here in our top right corner. It's that I squared is equal to -1. That's what makes sense when it comes to this, and that's what we're basing our whole belief system on for answering these questions. Now in this fraction I have two values which have I squared, and that's our plus 6I squared and minus 4I squared. So let's see how this might look if we now sub in -1 instead of our I squared. Might it make things easier for us? Alright, so I'm just going to bring it up here. And now what I have is that minus 12 plus 1 plus 6 times -1. I've gotten rid of the I squared. And on the bottom I have 9 minus 4 times -1. Okay, I can bring this down one step further. I get, my apologies, that should be 1I. Minus 12 plus I, okay, 6 times -1 gives me -6. On the bottom I have 9, and then I have minus 4 times -1. Well, a minus by a minus is a plus. That should give me a plus 4. Can tidy this up yet again. Minus 12, take away another 6. Well, that gives me minus 18 plus I. And then on the bottom I have 9 plus 4, which is 13. So this is our fraction completed. In a lot of questions what we'll see is they will ask us for the answer in the form of, I'll just write it here, x plus yi. Okay, they will ask us for it in that form, and they will specify that they would like x and y to be real numbers. So really what we have to do here is we can't have it as a singular fraction. It's just a case of pulling it apart for now. And what that looks like is we have minus 18 divided by 13 plus 1 over 13I. Okay, and that is equal to our original fraction of z2 divided by z1, or those two complex numbers divided by one another. Alright, this is considered to be kind of a long-winded question, but the whole foundation for it just stems from the conjugate of that complex number. If we can effectively identify it and put it in, we will see our lives hopefully get a bit easier. And it was really when we got to this point that transferring in -1 instead of I squared clarified things a bit better for us. Our takeaways from this video ideally would be our modulus. Here's our formula for it. It's the square root of a squared plus b squared. We did discuss where it comes from. It is a measure of distance, or a measure of length, basically of the line segment from the origin to wherever this complex number is placed on our Argand diagram. Should always be positive. The second takeaway we should have is division of complex numbers utilizes the conjugate. And an example here, if we have z1 is equal to a plus bi, then its conjugate is a minus bi. So there are two main takeaways hopefully from this video.